Okay, next is Minh-Ha from Linköping University, and he's going to talk about identity disentanglement for anonymizing faces. Minh-Ha.
Hello everyone, my name is Minh-Ha. I'm from Linköping University, Sweden. Today I'm going to talk about a framework for anonymizing faces. This work is carried out mainly by me and my supervisor Nicholas Carson. He is not today, so I will be representative and present the work. As you know, the facial data is raising significant privacy concerns because it's widely spread over the internet, especially the social network and surveillance system, etc. So we try to solve the problem of anonymizing faces. It appears that it appears in the first sight that this is very trivial problem, but usually for machine learning, for example, it requires high quality of data, and the facial domain is especially very complex domain. And what we're trying to solve the problem here is in the scale of data set. So we want to focus more on anonymization aspect of the problem. So in this work, we try to have a threefold approach. So basically, what it means is that we tried different spaces, different angle, and then have as much as control over the data as possible. So the first approach is in latent space. Latent space is some sort of latent or hidden space with a maybe in a by some sort of GAN model, for example. We try to have some sort of disentanglement. We try to separate what part is corresponding to identity, what part is for non-identity related. And if we can identify that, we can effectively hide the identity information. So latent space alone, it has some of the drawback, which I will present later. The next thing, the next approach is in pixel space. So basically, we have a higher level of control over the utility of the data sets, while effectively anonymizing the face. Also, this approach on its own had a little bit of drawback. And then finally, we consider the performance aspects of the process, and then we put every lesson that we learn into an end-to-end approach and into a final model. And so the main contribution of the work would be four bullet points, I think. So the first contribution is a threefold approach for anonymization. I think that we are the first to proposing this kind of approach. And then at the core of the contribution, I think that it is the disentanglement metric that we are proposing. The third contribution is the tunable privacy, which can be achieved by the full framework and end-to-end process. And then we consider the performance aspects of the problem. So for the framework, it has three main components, but they on its own, each component could be a solution for face anonymization. But together, we each of the components complementing each other, and we have a higher level of control and better privacy and utility trade-off. So the first component is identity disentanglement. The second component is masking face, and then the third component is squareness. So the first component will be mainly on latent space. The second component is on pixel space, and then the last one is a model for better performance. So you may not familiar with the term of the disentanglement. So this is on its own a research field in machine learning. So basically what disentanglement means is that if we have an image, for example, we project it into latent space, and then just changing small parameter or small direction in the latent code, we can change the appearance of the image. For example, if we have a face like a neutral face, and it could be we project it into the latent space. We change some sort of parameter or direction of the latent code. We can make the face smile while still be the same person. In this case, I just saw a reconstructed version. And we can do a lot of different kind of manipulation. But the challenge with identity here, that identity is composed like different feature, maybe lighting, different condition, etc. It composes the identity. For example, changing the smiles alone will not change the identity. Switching the pose of the image will not change the identity, things like that. So we try to have some sort of the magic. That is the first problem or the core problem. So we're using different kind of model to measure how much the identity had changed if we change certain component or item or direction of a certain latent code, and then we measure how much the attribute had changed. So each of the identity or attributes or feature, non-identity related feature will be measured separately. And we finally have a score where we try to maximize the identity difference and minimize the attribute difference. So in that way, we can effectively fight on finding which part of the latent code that is highly correlated to the identity, which part is not. And then we can effectively hiding the identity for information, for example. So I would like to comment here that it's not supposed, in this work, we mainly focus on facial domain. One of the reasons is that facial images or data sets is widely popular, but it could be, the work could be applied for other kind of biometric image. So the next thing is in pixel space. So the thing with the latent space is that sometimes you don't have the control over localization, which means that, for example, you change the face, but maybe the background had changed also, the hair has changed a little bit, etc. So within pixel space, we try to have a localization control of the which area of the face that we want to change, etc. So with another model to extract the facial mask, we can hiding a particular area of the face and then effectively swapping with a random face. The random face generator is a style generator, so it's totally random. And finally, even though each of the approach before has its own advantage, it also have usually have a performance issues. For example, we have to use some third-party component, and then the performance of the system end-to-end had to be depend on the performance of each individual component. So what we're doing here is that we try to put an end-to-end solution. So we had a lesson learned for identity disentanglement. We know which part of the latent code that is highly correlated to identity, which part is not. And then we try to build a model that try to swapping the original face with a random face that is generated by the system. And then we use the previous approach, which is identity masking, to prepare a data set. That data set is not perfect. It will always have some sort of artifacts, but it is enough for a ground truth for training this latent swapper. And eventually, we have an end-to-end system that given any face, we can effectively anonymizing the face and preserving high quality of the data set. So now here it comes to different evaluation. So most of the evaluation is again facial recognition or facial verification system. By verification, I mean that some sort of one-to-one match evaluation. So ROC curve is a popular metric for evaluating the performance of a facial recognition system. So this ROC curve, what it means is that if the facial recognition is good, then our ROC curve will have like the blue light that you see on the right hand on the left hand side. If it is like not good or totally random, unable to identify a match. It could be the line would pushing towards the diagonal. And so what the image and the table showing here is that our method effectively put the ROC curve close to the diagonal, and then it is more effective compared to some of the related work. Next is more on the recognition side or rank-based comparison. So in facial recognition, it is more relevant for one-to-end matching. So for this kind of evaluation, we use Microsoft APIs for this, and we build a facial recognition. We run the evaluation with different state-of-the-art anonymization method, and we show that with our result usually put the identity under protection into the rank of 1,000, for example, and it's usually outperform the state-of-the-art and effectively protect the facial identity. Another aspect of the data utility is attribute preservation. So you see in the bar plot here that the first histogram is the original from original data sets of some selected attributes. And then what we're showing here that our framework StyleID can effectively preserving the original histogram of the original data set, while the other related work usually shipping the histogram a little bit. And the third and the second result is some visual or quality results, where we show that with a framework we can effectively control over the attribute and correctly preserving a selected attribute like gender, pose, etc. Another aspect of the facial data set is identity diversity. So we also see so that the identity number of identity in the data set usually preserved when compared to the related work. Lastly, this is our conclusion. So we're proposing a feature preserving anonymization framework. We're proposing a disentanglement metric. We provide tunable privacy. And then last but not least is an effective method for produce high quality anonymized data sets.
Thank you so much, Minh-Ha. Okay, I'll start with the questions online while some of you might be preparing another question. Have you considered the usability of your anonymization? How easy would it be for users to anonymize their own images using your approach?
We're proposing this method for working with a lot of data sets, but usually if it works for n sample, it should be perfectly fine for one sample.
Okay. Any questions from the room? A very quick one while we're setting up. I think we've got an online presentation now, right? So, Brett, you're next, yeah. I'm just wondering, when you've done the identification evaluation bit, right? Have you considered the effect of the attributes themselves on the identification success rates? So things where, faces with glasses would be less prone to identification, or, people smiling, that particular attribute might contribute to the identification or not.
So that is some sort of higher level if we consider L diversity or this closeness of attributes. But for face, I think that we try to solving what the most important part, which is again the facial recognition, and maybe some recognition maybe cannot attributes though consider those attributes.
Okay, thank you. Thanks, Minh-Ha.